everyone. This is the second time I'm recording this video because the first time around, in the middle of the video, the audio cuts out. So we are going to record this for a second time. So this is the computational mechanics lab. This is a better title for this lab would be fluid-solid interactions, because we are simulating fluid flow and then we are applying the exerted pressure from the fluids to the solid. So we are essentially analyzing the interaction between the two. So first thing we want to do is to analyze the fluid part. So we just have to drag and drop the fluid flow module or Fluent. We are planning to use the design modeler CAD software that is built in Fluent. Just have to give it a little bit to open up. Okay, so this is going to be a very simple model. We are going to have a cylinder or a cylindrical shape with a radius of so here right now it says radius is 4 meters. You want to change this to 25 centimeters. I forgot to change the scale. Just have to scroll in, right? This is our circle, and we want this to be enclosed by a rectangle that will act as our control volume. So this is a circle and the rectangle around it, and this is your sketch. Okay, so we go to the modeling section. We want to extrude this sketch. Let's say the depth of the extrusion should be 1 meter. This is essentially going to be let's say a beam that connects two walls, right? That's how we are going to treat it in Fluence, in fluid flow analysis, CFD analysis. Okay, geometry is ready. Let's go to meshing. Again, we just have to wait for this to open up. Just have to give it a minute. So there are two things we want to do here first is to mesh the geometry we have, and second is to name the boundaries. So for meshing, the only thing we really want to change is this element size. By default is 0.28, so 28 centimeters, which is larger than our radius. We don't want that to happen, so I'm just going to set this to 10 centimeters and generate the mesh. Okay, this is not the best mesh. As you can see, there are problems around here, but it's fine for the purposes of this lab. Next step is to name the geometries. You want to change your selector to face selector and select all of the faces. Okay. Name selection. This is top wall. And then we can click on here again. See, this gives us an option to choose the top wall or the wall that is behind. So right click here, create name selection, right wall. Here it also gives an option for us to choose between, I guess, the right wall, the inlet, or the bottom, right? Depending on where you select. And we are going to see that in a second. So left wall, then we want to choose the bottom. So you just have to click on the vicinity where the bottom wall is, and gives you two options. Right? We are selecting the bottom wall now. This is your outlets. And the only thing that remains is the inlets. And also, I guess the most important part is the beam itself. Okay, let's check all of these selections. Top wall, right wall, yes. Left wall, bottom wall, right here. Outlets, inlets, right here, and the beam. Okay, mesh is ready. Everything, all of the boundaries are named. We are ready to go. Have to update this first, as is the case always with Fluent. Okay, and we want to change the CPU count to 4 or more if you have the full version. And again, if you are using the lab computers, you can't allow any of this. Just have to cancel them. I'm sorry. We already know how to deal with this part. In the general, we don't really need to change anything. The models is already at a viscous model. We don't really need to change that. And we want to make sure that the cell zones is going for fluids. This is actually, for whatever reason, it chooses the name of solid, but the material is air. So I'm not sure why it chooses this name solid. And we need to add an inlet velocity. The rest of this we have discussed before. We can either do, I'm going to do 10 centimeters per second. I think in the previous video I did 1 meter per second. It doesn't really matter. And there's nothing else we need to change. We can just go to initialize the problem, and run the calculations. You want to set the number of iterations to 1,000. We have our solution. Let's look at the contours of pressure on the beam, which is the area of interest. As expected, you get the highest pressure in the front, the lowest pressure is on top and the bottom. This is where the flow separation happens, and we also have a flow separation region at the back. Okay, so we're ready to go to the static structural module. Okay, static structural, right here, drag and drop. We cannot use the geometry of Fluent. We have to create a new geometry because in the static structure module, we are not interested in analyzing the contour volume around our beam. We are interested in analyzing the beam itself. So we have to create a new beam, but it has to be the same beam. So we just essentially just going to create a circle with 25 centimeters radius and go from there. Circle, dimensions, radius has to be 0.25. And sketch is ready. We can just extrude this 1 meter. We have to choose this correct sketch. I don't think we chose the correct sketch. Yep. No, we did. And then we extrude this for 1 meter. The the geometry is ready. Next step is to create the mesh. But before creating mesh, we can actually export the solution from Fluent and import it in the state structure module. So essentially just have to click on this and drag it to setup. That's how the transfer is done. That's the beauty of ANSYS, essentially. A multiphysics analysis is so simple. As simple as just doing a drag and drop. So you double click on the model. Again, we are interested in analyzing the beam here, only the beam. Okay, right here, the first thing you want to do is to check the material. Is a structural steel, geometry import, and we also have the imported load right here. We're going to get to it later. Let's do the mesh first. The element size, we had 10 centimeters over there. We can do 10 centimeters here or smaller, doesn't really matter. Because if your mesh is not the exact mesh as you had in Fluent, your software will just interpolate the data. You can right click on the mesh and update this to make sure the mesh is created. As you can see here, the analysis module, the static structure module, is in the same software as the meshing. The reason is the static structure module was the original module ANSYS built, actually. They later on added Fluent and all of the other software. Okay, so this is essentially just a legacy that was carried over. We don't really need to change anything here because it's somewhat simpler than ANSYS. The only thing you really than Fluent. The only thing you really need to do is to make sure you have the appropriate boundary conditions. Okay, so we just have to make sure that we are on the face selector, and we want to have two fixed supports on two sides. One is this one, and because they were connected to a wall, if you recall, and one on the other one on the other side. Okay, two fixed supports. Fixed one, support one, fixed support two. Okay, so then you have to create a boundary condition, a pressure boundary condition for the beam itself, and you have to select the beam, of course. We don't really need to change anything here. It has to be a mechanical base mapping. And for the rest of it, you want to make sure that your CFD surface is correct. The CFD surface, the CFD data we want to use was the data for the beam, which looks like to be correct. And then the next thing is to make sure that we actually capture the total deformation data, the strain, the von Mises stress, strain and stress data as well. Okay, and then we are ready to run this. You can change the number of the step size, you can change the number of iterations, you can change the degree of accuracy in everything. You can do essentially everything you did in Fluent as well here, but we don't really need to do this. Okay, so this is our stress, this is our strain, and this is our deformation. We can get an animation as well, but you have to keep in mind that this is a steady state operation, meaning that the forces on this does not change, and this animation is just a simulation of how your solution started from zero deformation and through a trial and error scheme got to this solution that the final solution that you have. So this is not real animation. The data makes a lot of sense. We have the maximum deformation we see is 4.1 times 10 to the power negative 14 meters. Makes a lot of sense. The structure is still, that's just 1 meter deep, shouldn't really bend that much. Okay, and that's it. Just present this data for the maximum deformation, maximum strain, and the maximum stress, and you write your report around it. Have Have a good day.